All right, Chemistry 3101. We left off last class looking at this practice the skill, and I said that would be the first thing that we would take a look at today. So the question says, draw the significant resonance forms for each compound below and indicate the major resonance form. Well, the first thing I noticed with this ion here is that we have a negative charge on our nitrogen, but we don't have any lone pairs, so we're going to put those in. And remember, it's okay to draw the molecule like that. Okay, if you're thinking, oh, they made a mistake, they're supposed to put the lone pairs. No, not necessarily. Okay, the author can freely leave those out because you are supposed to know that when nitrogen has a negative charge, it will have 2 bonds and 2 lone pairs. So there we go. So now we've got our lone pairs drawn in, and there we go. So let's start drawing some resonance contributors. Well, the first thing I notice is that we have an allylic lone pair, right? We have our lone pair, single bond, and then a double bond. So we can start by pushing some resonance arrows like this. We'll make a new bond here, and we're going to break this pi bond, and we're going to take those 2 electrons and put them right on to this carbon. And so we draw a resonance arrow. Remember, this is a double-headed arrow. It is not an equilibrium arrow. It is a resonance arrow. We start by drawing everything that hasn't been touched, is what I like to do. Now we have a double bond on our nitrogen. It still has 1 lone pair. We have a lone pair over here. We have a double bond here, and we have our double bond here, which hasn't been touched in any way. So there are formal charges in this molecule. Could anybody tell me, or could anybody tell me where the formal charge would be? There's one formal charge. Where would it be? Could anybody describe that to me over Microsoft Teams? Might not be the easiest thing to do. No, the nitrogen's not +1. The nitrogen is neutral, right? If we have a single bond here, right, we think about this nitrogen. Nitrogen has 5 valence electrons, subtract 3 sticks and 2 dots. That gives us a formal charge of 0. Yeah, this carbon will have a -1 charge, right? There we go, just like that. Remember, if we have an overall -1 charge here, right, this is -1, okay, that means that this is going to be -1, right? We're not going to end up with, a neutral species if we're starting out with something that has a negative charge. So now we've got a -1 charge overall. And now we can start drawing the other resonance contributors. Notice that we have another allylic lone pair here. So let's do that. So we'll start with making a pi bond, right? The head of the arrow ends between these 2 carbons, and now we're going to break this pi bond, and we're going to put that pair of electrons on this carbon here. We draw our resonance arrow. We draw our 6-membered ring like this. Now we've got a double bond here. We have another one here. I'm going to draw the condensed form here, put our lone pair, and now we've got the negative charge here on the carbon. So now we've got 2 resonance contributors, and I think we can keep going, can't we? Because we have another allylic lone pair. Here's our lone pair. Here's the allylic pi bond. So we'll draw our 6-membered ring again, like this. I'm just going to draw everything that remains unchanged. And let's do it. We're going to make a new pi bond here. Maybe I could try to end that exactly between the 2 carbons. And then I'm going to put my lone pair up here. So what will that give me? That's going to give me a double bond here and here. And now I've got my lone pair up here. That's the last resonance contributor. Okay, now if you're astute, you probably notice, well, I could draw, I could do this, but that's going to take you right back to here. Okay, that's going to take you right back to the first one. So we have a total of 4 resonance contributors, and we drew 3 new ones. Now, if I call these, let's say I call them 1, 2, 3, and 4, could anybody tell me which one of these would be the major resonance form? Right, there's only one of them that could be the major one. Could anybody tell me which one would be the major form based off of the rules that we looked at during the last class? Yeah, absolutely. It's the first one. Yes, this will be, this will be the major contributor, the major resonance form. Why? Because the negative charge is on most electronegative element, okay, which is a nitrogen in this case. right? Nitrogen lies to the right of carbon. It has an electronegativity of 3.0. And so, again, here we have the negative charge on the nitrogen. There's kind of a double whammy here. This is something that we haven't talked about yet, but it is something that we'll look at more so even in organic chemistry too. And that is in that this resonance contributor here, it's the only one where the aromatic ring is fully intact. There's the aromatic ring. You notice that the aromaticity or the aromatic ring is broken up in the other ones. And just to put this bug in your ear, again, I'm not going to ask you about this, but I'm the kind of person that likes to just give my students little tidbits of information along the way of things that you're going to see. You know, when we talk about an aromatic compound in organic chemistry, at least in organic chemistry 1, we draw the 6-membered ring and we say that's an aromatic, and it absolutely is. Benzene is an aromatic compound. Well, first of all, there are many other types of aromatic compounds. Like, let's say you draw something like this, and again, I'm not going to ask you about this in any way, shape, or form. This is called oxazole. This is also an aromatic compound. It doesn't look a whole lot like benzene, but the idea behind the word aromatic, the first aromatic compounds that were isolated by scientists did have fragrant odors. They did come from things like tree resins, and so they probably did smell good, and that's where the name aromatic came from. Since then, scientists have discovered many more aromatic compounds, many more aromatic compounds, and some of them have no odor at all, and some of them don't smell good at all. Okay, so aromatic now, aromatic actually means stable. So we could even put that in here. Aromatic just means increased stability. And we learn all about the rules for what renders a compound aromatic and what renders a compound non-aromatic, and also what's called anti-aromatic. And that's covered in organic chemistry too. So something to look forward to. Anyhow, let's take a look at the next one. We have a positive charge here on this compound. So let's start by putting this square bracket. Remember that these square brackets, what they mean is that all of these structures here, they're all really tsatzy, aren't they? But they all represent one thing. Okay, they all just represent one thing. They show the delocalization of the electrons, right? Because electrons, if they can move, they will. Well, let's take a look at this one here. The first thing I notice is that you're missing a lone pair on the nitrogen. Again, it's not a mistake or anything like that. They just left them out. And we have a pair of electrons right next to a carbon that has a positive charge. So we can dump those electrons into there to give that carbon a complete octet, and that would give us this compound where now we have the positive charge on our nitrogen, right? The reason that we have a positive charge on our nitrogen is because nitrogen has 5 valence electrons, subtract 4 sticks and 0 dots, that gives you +1. Okay, good. So we still have our charge of +1. Is there another resonance contributor that we could draw? Absolutely. Okay, absolutely we can. Well, how would we do that? We can push these electrons back onto this nitrogen to reproduce this. Now, I'm kind of doing 2 arrows at once here because that would put this positive charge here, and you can see that this is an allylic carbocation. So I can dump these electrons into here. So again, I'm doing 2 arrows at once. And what we end up with is something that looks like this. So we have our nitrogen that has its bond to hydrogen. Now it's got its lone pair back. I've got a double bond here. And now I've got my carbocation over here. So those are all the resonance contributors. Now, if I call these, I don't know, if I call them A, B, and C, there's one of them that is definitely the most prominent form or the most significant resonance contributor. Can anybody tell me which one it would be? And it's not a trick. It's something that I've brought up several times in the last lecture. And yeah, absolutely, Mackenzie, 100%. It's B, isn't it? Right? Could anybody tell me? Oh, all my students are killing it. Why is it B? The reason why it's B is because all octets are filled. All octets are filled. Right? In A and C, we have carbocations. That means that both of those carbons don't have complete octets, do they? Whereas in this species here, everything has a complete octet. Even the nitrogen, right? Even though it's got a positive charge, it still has a complete octet. Look, 1, 2, 3, 4, 5, 6, 7, 8. So it's got a complete octet. And there you have it, folks. That's the answer. All right, that's a pretty good practice problem, I think. Practice the skill. And you'll find that our textbook has these skill builders, which are really handy. They really help you hone your skills in whatever section we're covering. So I recommend taking a look at those. Anyhow, let's move on from there and talk a little bit more about the resonance hybrid. Remember when we have an allylic carbocation like this, I said we could draw these two resonance structures, or we could draw the resonance hybrid. I told you, I'm never going to ask you to draw a resonance hybrid. And but however, I did assign, or I do select some problems that involve the resonance hybrid. Why? Because it is important. It is important. And the resonance hybrid, what it represents the pi bond of an allylic carbocation being delocalized over all three carbons. Now, I'm not going to completely reteach this, what we covered during the last class or the class before it. I don't remember exactly, but you know that there's a p orbital here because this carbon is sp2 hybridized. This carbon is sp2 hybridized, and this carbon is sp2 hybridized. And what that forms is that conduit, if you will, where all these orbitals overlap to form this type of molecular orbital. And so since all the orbitals overlap, the pi electrons occupy the whole thing, right? They take up all of those three p orbitals. And so this is how we would represent the resonance hybrid. Instead of drawing individual pi bonds like I have here and here, I draw kind of a pi bond that's spread over the entire thing like that. Instead of drawing a full-on carbocation like I have here, I draw partial positives because both of the carbons have that partial positive character. Remember, the molecule is not vibrating back and forth here. These resonance structures represent the overall hybrid. And so we use the resonance hybrid to help us explain that. Well, let's talk a little bit more about localized and delocalized electrons. You hear me say the word localized, and you've heard me say the word delocalized this morning. So what exactly does that mean? Localized, it just means if you think that, you know, if you live in one locale, in one location, what does that mean? You stay in one place, right? So localized electrons are ones that aren't moving. They're not participating in resonance. They're just, you know, where they are. If you think about a molecule like ammonia, okay, if we just draw the Lewis structure of ammonia, NH3, right? There's a lone pair there, but is that lone pair going to go anywhere? No, there's no allylic pi bond. There's no carbocation to dump the electron. There's nowhere for those electrons to go. So those are completely localized, right? They're just stuck in that one place. Delocalized electrons, however, are electrons that are participating in resonance. It says to be delocalized, a lone pair of electrons must be adjacent to an atom with an unhybridized p orbital, right? That's something that we've seen already. Now, if you look at this lone pair on an amide, right? An amide is a functional group that we've covered already, and I'm sure you've spent some time practicing your functional groups. It says here that the lone pair on the nitrogen is delocalized because it's next door to a carbon with a p orbital, right? If we have a pi bond between this carbon and this oxygen, right? There's a pi bond there, right? The first bond is a sigma bond, remember, and anything after a sigma bond is what? A pi bond. Well, pi bonds are formed when you have two p orbitals that overlap side by side, right? This is how we make a pi bond. So that means that there's a p orbital on here and there's another p orbital on here. Now, I can't draw them touching because it'll look like heck, but there you go. There is that unhybridized p orbital. So that means that lone pair can participate in resonance. So it is delocalized. Well, what's the significance of all that? What's the significance? If you think about the hybridization of that nitrogen based on what I taught you, okay, if you look at the hybridization of the nitrogen here, what's its steric number? Its steric number is 4, right? You've got 3 single bonds and a lone pair. So that means it's got a steric number of 4. That means it's sp3 hybridized, right? But if you look at the resonance structure, and everybody should be able to push these arrows to draw this resonance form of an amide. Well, hold on. Here we have 3 sigma bonds and no lone pairs. So here it's sp2 hybridized. Which one is it? Okay, it's a really good question, isn't it? Which one would it be? It says here, since that lone pair is delocalized, which is only possible through the overlapping of p orbitals, it has to be sp2 hybridized, right? Think about it. The only way that this lone pair could be delocalized is if there is an unhybridized p orbital on here, which would mean that that nitrogen is in fact sp2 hybridized. Now, I've taught this class many, many times, okay? And we're kind of, you know, in the dusty end of chapter 2, right? We're getting towards the very end of the chapter, and students, and again, I was a student for a long time. I'm totally guilty of this. You know, I'd get to the end of a chapter like, oh, the end isn't important. You know, it's the beginning. That's where the meat is. Well, look, I just want to point something out to you, and maybe you would never do that. Okay, I'm sure all of you are better students than I was. But anyhow, this is one of those points that comes up from time to time in organic chemistry, and oftentimes when I ask students about it, they'll forget it. So just make a mental note of this right now, that this is a very important concept, that you know that the nitrogen of an amide is sp2 hybridized. So in fact, it is sp2 hybridized because it's going to come up again. And if you're the kind of person who maybe is doing a biology degree or a biochemistry degree, well, you're going to spend a lot of time looking at proteins and enzymes, right? You're going to spend a lot of time looking at amide bonds. And some of the interesting properties of amides, some of their rigidity, and you're going to learn about the conformations of proteins and enzymes, and you learn about the induced fit model and the lock and key model. Anyhow, that's neither here nor there right now. But the fact that that nitrogen is sp2 will be important for you, not only in this class, but also in a biochemistry class. So something to think about there. Now I want to show you another interesting example. And this is a very particular example that I want you to know, okay? And know might be synonymous with memorize for you, and there's no problem with that. I memorize things all the time, okay? A lone pair doesn't participate in resonance if it can't overlap with an adjacent p orbital. Then it's localized. So this is a very particular example, and again, it comes up a lot in organic chemistry, so we want you to know it. In fact, there might even be a question about this on your final exam. I remember a couple of years ago, I gave my students an ACS final. I perused the questions because I don't keep a copy of the ACS final. I'm not allowed to, but I look at it enough that I can memorize part of it, you know. And I remember one of the questions on it was, what's the hybridization of the lone pair on the nitrogen of pyridine? Okay, what's the hybridization? And if you look at the structure of pyridine, you might think, you know what, man, I have a lone pair. Look, then I have a single bond, then I have a double bond. I can draw a sweet resonance structure like that. But in fact, you can't. Okay, now why aren't you able to do that? Right? There's a good reason why you can't. Now the answer is just below here, but if you think about the structure of pyridine, it has double and single bonds that alternate, right? In these pi bonds. If this is, and it is, if this is, where's my red pen? If this is a pi bond, right? This here is a pi bond. That's formed from the overlap of two p orbitals. That means you've got a p orbital on here that's overlapping with this one, okay? And that p orbital has, or this p orbital has one electron in it, right? And then this one has another one that's going to overlap to form the pi bond. Well, that means that the lone pair is not going to be able to overlap with anything, right? Because that lone pair is going to be in another orbital that is going to be perpendicular to the plane of the molecule. So here's the lone pair right there. So what's the significance? The significance is that the hybridization of the lone pair is sp2. Now, if you just want to flat out memorize that, there's no problem, okay? Yeah, it's not a proper, well, technically, there's not too many bonds to nitrogen here because it has a complete octet, right? You think about this, it has 1, 2, 3, 4, 5, 6, 7, 8. It does have a complete octet. It doesn't exceed the octet rule. That's not the point. The point is that you can't draw that resonance structure because in order for resonance to happen, and this is something that we've looked at several times, you've got to have the overlap of the p orbitals, right? They all have to be overlapping, right? Just like I've drawn here. And you can't have overlap of the orbital that holds the lone pair with all the other p orbitals. It has to be perpendicular, right? Because there already is an unhybridized p orbital on the nitrogen that is participating in the pi bond, right? This is the one that's participating in making the pi bond. So this one has to be perpendicular to the plane, and therefore it's sp2 hybridized, right? That nitrogen has a steric number of 3, doesn't it? Right? It's got 2 single bonds and a lone pair. So it's It means that it's a hybrid. Its hybridization is sp2, but the lone pair is not in a p orbital, so it cannot participate in resonance. Okay, it's in an sp2 hybridized orbital. There you go. So the example of pyridine tells you, okay, pyridine tells you that you can't just assume that a lone pair is delocalized because it's next door to a pi bond, right? If you look at pyridine, you might think, oh, I can draw a resonance structure, but you can't. And in order for you to know that you can't draw that, in order for you to understand why you can't do that, you have to understand this. Okay, you can't connect the dots. I mean, you could just memorize it and kind of take the hammer and tongs approach and just say, I'll just flat out memorize that it's sp2. And I remember one year I must have preached this really hard to my organic chemistry students because I got them in August for organic chemistry 2. And I said, hey, what's the hybridization of the lone pair on the nitrogen and a pyridine? And they were like, sp2. So I said, wow, I must have repeated that a lot in class. Anyhow, so as a general rule, you can assume that when an atom possesses a pi bond and a lone pair, they both can't participate in resonance. So this is another handy point right here. When you've got both a pi bond and a lone pair, there's no way that they can both participate in resonance. And as always, if there's no p orbital next door, then it's going to be localized. Just like if you look at this lone pair here on this nitrogen, there's no p orbital. There's no p orbital here. There's no p orbital here. And this carbon is sp3 hybridized. There ain't no p, pardon my language, there's no p orbital next to that. So that lone pair is totally localized. Now, if we look at the other lone pairs, okay, and I'll draw them in, I have a lone pair here and I have a lone pair here. But remember this rule here, it says if the nitrogen, or if an atom possesses both a pi bond and a lone pair, they're both not going to participate in resonance. So this nitrogen has a lone pair and it has a pi bond, right? This is the pi bond, this is the lone pair. There's no way they can both participate in resonance, right? You have a p orbital on this nitrogen, but that's making the pi bond. So there, that tells you that this lone pair is not going to participate in the resonance, okay? So that is a localized lone pair. And then this one here is delocalized because it is allylic to a pi bond. So we could draw, we could draw a resonance form like that, and I'll let you try and draw what the resonance contributor would look like. So that's the difference between localized and delocalized lone pairs. And that brings us to the end of chapter 2. Well, with all that in mind, I thought we would spend some time taking a look at some practice problems. And there's a particular problem that I wanted to look at from the end of the chapter. And it is question number 2.63 and 2.61. But before we do that, let's try something a little more fun that might not be as much of a brain bender this early in the morning. Let's see here. So I'm going to start this morning's practice by drawing a molecule for you. So I'm going to draw a molecule, and I want you to see if you can recognize some functional groups. You probably noticed a couple already, but I'm just going to finish drawing it here. So just give me a few minutes. All right, here's the first molecule. I'll give you a few minutes and I'll draw another one down here. We'll see if we can recognize some functional groups. All right. So the molecule that I have drawn in black, could anybody tell me which functional groups they recognize in this molecule, if any? And I'm sure you do. Yeah, absolutely. Mackenzie says an alcohol. I agree. Here we go. We have a hydroxyl here that's attached to a carbon, so this is an alcohol. Absolutely. Yes. All right, Jonathan says an aromatic. Absolutely. Here's the only aromatic ring in the molecule. So we have an aromatic here. Wow, Warren, you got a bunch here. Aromatic, amide, alcohol, alkyne. There's an alkyne. There's no amide, but there is an alkyne. Alkyne. Remember that an amide is when you have a carbonyl and then you have a nitrogen attached to it, like this. So this is an amide. What else? Oh, Kelly says an amine. Absolutely. Yes. There's an amine right here. So amine. There's two more. Let's see. Sorry, I'm trying to look at my chat here. Yeah, there's a couple more functional groups in here. Yeah, thanks, Mackenzie. Absolutely. There's a ketone. Yep. This is a ketone right here. Ketone. And then there's two more. Yeah, Abby, nailed it. Yep. There's two alkenes, aren't there? There's a double bond here and there's a double bond here. So these are both alkenes. Yes, absolutely. So there's what? 1, 2, 3, 4, 5, 6, 7. 6 different functional groups, but there's a total of 7 in this molecule. Something that we'll look at, I don't know, much later in the class would be this kind of skeleton here, where you have these 3 6-membered rings and a 5-membered ring attached to it. We call this the ABCD ring structure like this. This is actually a steroid skeleton, which is something you kind of get used to seeing, especially if you're into biochemistry. And I see that cholesterol has that same skeleton, or many contraceptives will have that skeleton. Anyhow, let's take a look at the one in blue. Does anybody recognize anything in the blue molecule? We'll call it that, the blue molecule. I don't know what the name would be. Yeah, absolutely, Abby. Yeah, absolutely, 100%. There's definitely a thiol here, isn't there? So this is probably some kind of foul-smelling compound, right? Jonathan says a ketone. He's absolutely correct. There's a ketone here. Yes. Any other ones? I realize it. Oh, Janahan's got a whole bunch here. Thiol, ester. So there's no ester. Amide. Yes, there's an amide. Absolutely. There's an amide right here. So amide. There we go. Yeah. What else? Oh, yeah, there's an ether. Absolutely. So this here is an ether. Did somebody unmute their mic? Was there something that you wanted to say? Sorry.
Somebody already said it, but that's what I was going to say.
All right, good. Okay, cool. And then Kyla says, I see everybody screaming at me, alkene. Yeah, you're right. There's 3 alkenes in the molecule, isn't there? There's 1, 2, 3. So these are all alkenes. You know, when you have an alkene, when they're conjugated, so let me show you what conjugation means. You know, in an aromatic ring, how the double and single bonds alternate, right? It goes double, single, double, single, double, single. Well, you could have the same thing in an alkane like this. You could have double, single, double, single, double, single, right? When you have those pi bonds and sigma bonds alternating, so alternating pi and sigma bonds, that's called conjugation. Conjugation. And if you have a compound that's ultraviolet, or it can be viewed under ultraviolet light, it's going to have conjugation. So that's why in the lab we work with so many compounds that have conjugation, because then you can view them under ultraviolet light. So that's one word I wanted to teach you, conjugation. Another word that I don't think ever comes up in our textbook, and if you're eye rolling me and just saying, oh, Mr. Dion, why are you teaching me stuff that's not in the textbook? Trust me, it's cool, okay? And it's important, because I'll probably use these terms from time to time. Let's say you have 3 carbons like this, 1, 2, 3 carbons in a bond line structure. We're going to learn later on in chapter 4 that this is propane, just like the propane in a propane tank. If you take that and you add 1 carbon to it, it's called like going from, or just adding a carbon. And obviously this is not a reaction, even though I've got a reaction, or you can't just magically grow carbons like this, but this is called a homolog. Okay. So let's say you drew, I don't know, let's say you drew this compound. You had this, and then you added 3 carbons to it. And then I said, draw the homolog. all I would mean is that you add an extra carbon on it, and that would be the homolog. Okay, it just means you add an extra carbon. Okay, it's a very common term that's used by organic chemists, so it's not some often left field thing I'm trying to teach you to boggle your mind or something like that. A homolog. Well, let's take a look at. I really wanted to take a look at question 2.61. It's kind of a long problem, but I think it's worth taking a look at it. Uh, Now, this is, kind of where there's a deficiency in teaching remotely. There's no, personally, I feel like there's no substitute for being with my students in the classroom. I really enjoy being face to face with my students because then I can walk around and see how you're doing. But if I can encourage you right now, would be to try this problem with me. It's question 2.61 from the back of the book, and do not look at the solutions, okay? Do not look at what they've drawn. But they started with this interesting looking molecule here where you have an aromatic ring, you have a hydroxyl group on here, I'll throw in the lone pair, and then you have this chain coming off of it here, and the chain is conjugated to the aromatic ring. Remember the word I used, conjugated, right? You got pi, sigma, pi, right? So sigma, pi, right? The whole thing is conjugated. The entire molecule is conjugated. Every pi bond and sigma bond, they all alternate. But what it asks us to do in the problem, I'll read it for you. It says, use resonance structures to help you identify all the sites of high electron density. So any place that there would be a delta negative, so wherever there would be a delta negative in the molecule. But all I want to do first is just focus on drawing those resonance structures. Now, again, we're on Microsoft Teams. It's not easy to answer some of these questions. But could anybody give me a clue as to where I would start drawing resonance forms here? And I'm sure there's somebody who's probably faster at it than me by now. Where would you start here? I'll take any suggestion. Yes, absolutely. Couldn't have described it better myself, Mackenzie. Mackenzie says start with the lone pair on the oxygen. Why did Mackenzie say that? Because it's the only place you can start, really. You've got a lone pair, and it's allylic to this pi bond. So let's give it the old college try. Let's start there, right? And Mackenzie would say, well, this is what you would do, Mr. Dion. You would take that pair of electrons, you'd make a new pi bond here, right? And then you'd move the lone pair over here like this, and you'd be 100% correct in stating that. So let me try and draw. I'm going to draw the skeleton and just copy and paste it just to save myself a little. That's not very pretty, is it? I might need one of those. What are they? The templates that you can buy that help you draw molecules. Later on, when we learn how to draw what's called a chair, students oftentimes will want to use those templates, but I recommend, learning how to draw yourself, and you're all capable. I teach it to my students, and then I go look at what they've done, in class sometimes, and I'll say that's better than I could do. I have some students who are really talented at drawing structures. Anyhow, so let's draw what we've got here. If you ever get lost or you just get bogged down in these kind of problems and think, oh man, there's so many bonds here. Why don't you just start by filling in the stuff that's not touched? This pi bond didn't move, this pi bond didn't move, this pi bond didn't move, this pi bond didn't move. All you did was manipulate some electrons around here. So now you're going to have a new bond here. The oxygen still has the hydrogen, and it's only got one lone pair on it, like this. And then you took a pair of electrons and put them onto this carbon. So now you have to evaluate the formal charges. There are formal charges. There are two of them. You have a positive charge on this oxygen, and you have a negative charge over here on this carbon, like that. Well, now we've got the same pattern that's going to occur over and over. We've got an allylic pi bond. So we're going to take that lone pair of electrons. Let me get my red pen here. We're going to make a new pi bond. We're going to break this pi bond and put a pair of electrons down here. So let's take this guy. We'll move it over here. We'll draw a resonance arrow. Remember, it's not an equilibrium arrow. This is not showing electrons vibrating around. We're just trying to draw or represent the delocalization of all of the electrons. So let me draw this bond in. Again, my positive charge is going to stay here. I've got a new pi bond here. This one and this one weren't touched. And now I've got my lone pair here. Let's keep going. Now we've got an allylic lone pair. We're going to do the same thing over. Okay, we're going to draw a resonance arrow double-headed arrow like that. That's the proper way. We don't want to be amateurs here. Okay, we want to draw things correctly. There we go. Put in our lone pair. Like that. We still have our positive charge here. And there we go. Just to kind of as an aside, you know what? You notice that you start out with a neutral molecule, right? There's no charge. So if you draw a resonance structure, it's got to be neutral, doesn't it? Okay, if you end up with something that's got a negative charge overall, you know you went wrong somewhere, or you left something out, right? So let's keep going from there. Make sure I have enough of these. All right, there we go. Let's draw some more curved arrows. We've got another allylic lone pair, and then we're going to put a pair of electrons right on here. So I'll draw, this is kind of wonky the way I'm drawing it because I'm running out of space here, but you get the idea. We'll condense this like that. Now we've got a double bond here. We've got a lone pair here, so we're going to have a negative charge. And then we have one more resonance structure that we can draw, don't we? We can put this lone pair to make a double bond here, and then we put the pair of electrons out here, and that's going to be, that's going to be the end of it, isn't it? That's all of them. We have a positive charge here. There we go. Double bond here, lone pair out here, and there we go. Now we're done. We've drawn all of the possible resonance contributors. So there's a total of what? We got 1, 2, 3, 4, 5, 6 overall, including what we started out with. So if we redraw the molecule, now I want to try to squeeze them all in here, so even though there's a page break. If we redraw the original molecule, so let's do that. We can represent where all the partial negative charges are, right? You've got a partial negative charge here. You've got another one over here. You've got one here, you've got one here, and you've got one here. So the way that we would represent that, let me show you, is you would say, I've got a delta negative here. And what you're going to see is that it's going to skip a carbon, go to the next carbon. Skip a carbon, it'll go to the next carbon. Skip a carbon, it'll be on the next carbon. And skip a carbon, it'll be over here. So those are all the sites of high electron density in this molecule. Kind of cool, huh? Give me a thumbs up if you understand, or even if you find that helpful. Does anybody find this helpful? I don't want to go over tons of problems if my students don't find it interesting, or if my students are just like, you know what, I understand, Mr. Dion, can you move on to something? Because if you all want to move on to something else, I'm happy to do that. I like practicing. Is this helpful for anyone? Okay, cool. All right, good. All right. And something else that you could do after class would be, since I do my best to post the recordings of these lectures to my YouTube channel, what you could do is say, hey, I want to try that problem again, find it in the video, stop it or pause it, try it yourself, to make sure you can do it. And then if you get stuck, you could take a peek at, what I've done and see if that can help you out. Let's try another one of those. I didn't plan on doing question 2.60, but I think it's worth it. Let's try it quickly. I'm going to move a little quicker this time, okay? This is question 2.60. Again, I didn't plan on this one, but I'm just kind of looking here at my textbook, and I think it's a good one. It says, use resonance structures to help you identify all the sites of low electron density in this compound. So let's draw the compound. It's got an aromatic ring in it, and it's got this conjugation over here, and then it's got this here. Notice, remember I taught you the word conjugation a few minutes ago? Look, double, single, double, single, double, single, double, single, double, single, double, everything's fully conjugated. Okay, it increases the stability of the molecule, and it will help it to absorb electromagnetic radiation. And yeah, that's neither here nor there right now. All right, much like the previous problem, where I started off with the last problem was I asked my students, where in the heck would I start? Could anybody tell me where to start here? It's kind of an interesting molecule. I'm just going to draw the skeleton while you're busy telling me where I can start here. Would anybody tell me where I might start? Yeah, thanks, Kelly. Absolutely. You're 100% right. Kelly says, start on the oxygen, Mr. Dion. That's Did I make a mistake in my skeleton? I think I did. There's 1, 2, 3, 4. 1, 2, 3, 4. Oh, yeah, I'm missing 2 carbons. There we go. That's better. All right. Excellent. Excellent. So let's see here. Copy. There we go. And paste a couple of these guys over here. All right. So, like Kelly said, she said, I think you should start here on the oxygen. Why? Because there's a difference in electronegativity between carbon and oxygen, and there's a pi bond in between the two. So all you have to do is break that pi bond. Now you've got 3 lone pairs up here. You've got a negative charge here. You've got a carbocation there, and you've got all of your conjugation in your ring like that. Now you can start drawing some resonance structures because now you've got what? An allylic carbocation. Right? So all you have to do is draw one curved arrow at a time. So we push one arrow like that. Let's draw everything that remained unchanged. Here we go, this one. And we still have our negative charge over here. We've drawn a pi bond here. And so now we've got our positive charge over here. Let's draw another curved arrow. This is going to take a while to draw all of these, but let's go for it. I've got another allylic pi bond. I'm going to have a lot of allylic pi bonds, aren't I? So let's do it again. We'll draw a curved arrow like this. Now we've got, we've got all of these lone pairs that are never going to change. We've got a double bond here. Now we've got a double bond here. Now we've got our carbocation over here. We draw in all our pi bonds, and let's keep going. We're going to draw another curved arrow like this, which is going to push the positive charge into the ring. Then look at all this conjugation that you're going to have out here. There's your negative charge. We can draw another curved arrow because we've got another allylic carbocation. That. Go. Alrighty. That. There we go. Let's keep going. You know, these might seem time consuming, but they're worth doing because it'll really help you master drawing resonance structures. You'll be the master of resonance. All right, if that's a thing. Anyhow, so there we go. So we dump those electrons in there. We have our positive charge over here. We keep going. Now we've got our pi bond over here. Our carbocation is here. Draw all the conjugation like that. And that's it. That is all of the resonance structures. Because if we drew one more, we'd end up right back basically to here, right? If you don't believe me, I'll show you what I mean. I'll just use a different color arrow this time. If you draw this curved arrow here, then you just end up restoring the aromatic ring is all intact again. Now you've got a carbocation here, right? Like this. And this and this are the same. And you might be saying, well, come on, this aromatic ring isn't identical to this. Yes, it is. Even though the double bonds aren't exactly in the same place, it's still identical. It doesn't matter how you draw them. And so that was our last resonance contributor. And so now if we were to take the time to draw the molecule, so let me just, I'll erase all this. I take this and I redraw my molecule. Then we can draw in where all the partial positive charges were from the get-go. So we had this. And take a look. You've got a delta plus here. You've got another delta plus here, another one here, another one here. right? And they keep skipping around like that. They're going to alternate like that. So those are all the sites of partial positive charge. So a good organic chemist, he or she should be able to look at a structure like this and know exactly where all the sites of partial positive charge are, or low electron density is the way they framed it in the textbook. There we go. Let's try one more. This is question 2.63 from our textbook. It's the last question before you get into the integrated problems, which are, I don't know, questions that involve, chapter 2 and other chapters, added together. So we have this interesting compound here, which I'll draw. It's got a nitrogen in the ring, but it's not aromatic, is it? It says enamines are compounds with an amino group attached to a double bond and are electron-rich alkenes that have important synthetic applications. Draw the major resonance contributors for the enamine show and show which sites on the structure are most electron-rich. So when you have a nitrogen with, let's say, you've got two R groups, you've got a lone pair, and then you have a double bond like this. Okay, we'll call these R prime. This is called an enamine. Anyhow, it's something that we don't look at in organic chemistry 1. However, enamines do show up in organic chemistry 2. But you see how the textbook loves to introduce you to little things like that all along the way. All right, so we've got an allylic lone pair here on our enamine. So we could start with that. We could push these electrons here to make a double bond, and then we can move these electrons onto this carbon. So let's draw our curved arrow. I'm going to draw my 6-membered ring as neatly as possible, or at least as neatly as I can. We have a negative charge here. Now we've got a double bond to this nitrogen, like this, and we have a positive charge like this. We can draw another curved arrow like this, and we can draw the last resonance contributor, which would be this guy. So we have our positive charge on our nitrogen, we got our double bond, and now we have our negative charge like that. So if we start with the original molecule, which is this guy here, that's not very pretty, is it? Let's try it a little bigger. Our initial molecule was this enamine. What are the sites of negative electron density? Well, there's one here, and then there's one here in the molecule. And the reason that's important, I would say, is because you have to be able to predict the reactivity of organic molecules. That's our goal, really. I mean, we're not there yet. That takes until you get about halfway through organic chemistry 1. But ultimately, you want to be able to look at a molecule like this one and predict how it's going to react. When I was in graduate school, one of the professors that was in the chemistry department where I studied told me a great, an interesting story one time. He was an expert in sulfur chemistry, and he said, one day I was sitting in my office, and this guy shows up with a briefcase, and he says, he showed me a molecule. He introduced himself, and he said, hey, if I show you a molecule, can you tell me what you think might happen, with this molecule once it gets inside the human body? And he said, sure. So he said, show it to me. So the guy showed him a piece of paper. He said, here's the molecule, and it had sulfur in it. He says, what do you think is going to happen? You're a sulfur expert. And the professor looked at it and he said, well, based on my knowledge, it's going to do this, and then it'll do this and this, and he basically explained how he thought it would react inside the human body. And then the guy said, okay, so based on what you just told me, I'm wondering if I could pay you $5,000 a day to be a witness in court, and testify as to what you think is going to happen, and he said, I will accept, I will accept that. So that's an example of being able to predict the reactivity of a molecule, and getting a little bit of a payout for it.